All right, here's the second example we're going to look at with the method of Frobenius. All right, so first off, we're solving 2x squared y double prime minus xy prime plus x squared plus 1 times the quantity y equals 0. All right, so if I divide off the 2x squared, I get y double prime minus 1 over 2x y prime plus x squared plus 1 over 2x squared y equal to 0. So my big P function, the coefficient of the y prime, is negative 1 over 2x. If I multiply by x, that gives me negative 1/2, which means my a sub 0 is going to be negative 1/2. Big Q, x squared plus 1 over 2x squared, if I multiply that by x squared, I get 1/2 x squared plus 1/2. All right, so b sub 0 then is going to be the constant term, and that's 1/2. So we get a b sub 0 equal to 1/2. All right, so using those two values in the indicial equation, we get r times the quantity r minus 1 minus 1/2 r plus 1/2 equals 0. We clean that up a little bit, and we end up with 2r squared minus 3r plus 1 equals 0, which I can factor. And then I get my roots for r is going to be 1/2 and 1. All right, so we know what the roots are going to be, but we'll still have to go through the process of making the substitutions and simplifying this. So we've got our y term, our y prime term, and our y double prime term. So we're going to make these substitutions into the differential equation. And we'll start off with, I'm going to go ahead and distribute the 2x squared here. So we've got the summation of 2 times n plus r times n plus r minus 1 times c sub n x raised to the power n plus r minus 2. Right, that's from the definition. And plus 2, that's from this x squared right there when we multiply that in. All right, so that'll just end up being n plus r. The next term is just minus the definition of what y prime is. And then the next term, we actually will have to multiply by x squared and then multiply by 1. That's why we're getting 2 more terms here. So this is the one that's multiplying by x squared, and there's the x plus 2 there. And then this is the term that's just multiplying by 1. This is a 2 up here in case anybody's looking at that. That kind of looks like a 1. So this is minus 2. All right, so this is minus 2 plus 2, so that's just n plus r. This next one has the minus 1 plus 1, so that's just going to be n plus r. And then we've got this third summation is going to have n plus r minus 2. All right, so we got that, or sorry, n plus r plus 2. And then this last term is n plus r. So we actually have 3 terms, this one, and this one, that actually start with n plus r. So if we plug in n equals 0, we actually will start off with the term x plus r. Unfortunately, my fourth summation here, that's this one, this starts off with an n plus r plus 2. So if I plug in n equals 0, I actually have r plus 2. So that means we're going to have to start at r plus 2, which means I'm going to have to extract the first 2 terms out of the 3 that start at n plus r. So we'll be going ahead and extracting the first 2 terms out of all 3 of those summations so that everything's starting at the exact same place. Okay, so after we extract those, so here's the first one. We let n equals 0, and we plug that in, and we get 2r times r minus 1 times c sub 0 x plus r. And then we let n equal 1, and we plug that into the summation term, and we get 2 times r plus 1 times r times c sub 1 x to the r plus 1. So we've got that. The next summation, we're going to do the same thing. Let n equal 0, and then let n equal 1. And we'll get this term, and then we'll get this term. And then we'll do that on the last summation. We'll let n equal 0 and get this term, and we'll let n equal 1 and we get this term. Then we can go back and say, all right, well, what's left of the summations that we had, right? So get rid of all this Okay, so all those n plus r terms then, I can put all of those into the same summation, and so that's what we're getting right here. So we get 2 times n plus r times n plus r minus 1 minus n plus r, the quantity n plus r, plus 1. So that'll be c sub n x to the n plus r. And then we'll have the other summation then 0 to infinity c sub n x to the n plus r plus 2. So notice here that this summation got shifted to a start point of 2, and now when we plug in n equals 2, this one will start at r plus 2, and when we plug in n equals 0, this one will also start at r plus 2. So now they're starting at exactly the same spot. Okay, so that means on the first summation, I'm going to let k equal n, and on the second summation, I'm going to let k equal n plus 2, which means all the n's will get replaced with k minus 2's. Okay, so I've simplified the c sub 0 and the c sub 1 term, so we've got 2r squared minus 3r plus 1, which should come as no surprise. That's exactly what we got when we worked that out before we ever started the problem. The other term then is 2r squared plus r times c sub 1 x, and now we've adjusted the k's, or sorry, we've adjusted all the n's to be k's, so everything that had an n in it is going to change. So we've got c sub k now, c sub k minus 2. So everything has changed to k's instead of n's. And notice I've also factored out that x to the r term, so I don't want to worry about that as I'm working through this problem. Okay, so we already knew that r was a half and 1, but here's, once again, you can get it this way also. So 2r squared minus 3r plus 1 equals 0, and that'll give us r as a half and r as 1. And we get the expression for the c sub k term is going to equal negative c sub k minus 2 over this complicated expression, and that's for k equals 2, 3, and on and on and on. So c sub 0 and c sub 1, at this point, we don't have any real sense of what those values are going to equal. All right, so we're going to let r equal a half. We always start with the smaller value. And so if I make all those substitutions in for r, I end up with c sub k is going to equal negative c sub k minus 2, 2 times k plus a half, k minus a half, minus k plus a half plus 1, which if you do a little algebra on that, that will simplify to k times the quantity 2k minus 1. So you got to multiply things together, combine like terms, and you will eventually end up with that, and that's for k equals 2, 3, and on. Okay, so we start by just saying c sub 0 is c sub 0, and c sub 1 is c sub 1. But we do have, with c sub 1, we do have the case that we've got 2 times r squared plus r c sub 1 equals 0 if you look back to our summation equation. Now 2r squared plus r is never going to equal 0, right? Because if r is a half, you can plug that in there and you get a half plus a half, you get 1. So the only way that's going to equal 0 is if c sub 1 equals 0, which means we've got to set c sub 1 equal to 0. All right, so then following the formula, so now we've got a value for c sub 0 is just going to be whatever it is. C sub 1 is actually going to be 0. And now we've got c sub 2 is going to equal, and we're just plugging in, this is for k equals 2. So we get 2 times 4 minus 1, or 2 times 3 is 6. So we get negative c sub 0 over 6. So we'll go on and we'll say, all right, k equals 3, and that gives us negative c sub 1 over 18, which is 0, so c sub 3 is 0. C sub 4, then, we make the substitution of k equals 4, and we get 4 times 8 minus 1, so 4 times 7 is 28, and so we get negative c2, and c2 is negative c sub 0 over 6, so we end up with c sub 4 equals c sub 0 over 168. Which gives us then our first solution, y sub 1 is x to the 1/2. So remember, we factored out that x to the r term, so that's always going to be multiplied out front. So x to the 1/2 times the quantity 1 minus 1/6 x squared plus 168x to the 4th plus whatever the other terms are. All right, then we let r equal 1. And c sub k still equals the same thing, but notice that, it cleans up to this again. Okay, which is a little bit different than what it was before. Okay, so we've got a slightly different formula for C sub k. All right, so once again, C sub 0 is just C sub 0, and C sub 1 is 0 still. So we get that C sub 2 is going to equal negative C sub 0 over 10. C sub 3 is 0. C sub 4 is C sub 0 over 360. So we get our second solution, which is x to the power 1, which is the value of r, times the summation of 1 minus 1/10 x squared plus 1 over 360 times x to the 4th. Okay, and then our general solution, so we always express the general solution as y equals some constant times y sub 1 plus some constant times y sub 2. So we get our general solution. Y is going to equal a sub 1 times x to the 1/2 times our y sub 1 plus a sub 2 times x to the 1st times our y sub 2. So that's our general solution. Okay, so some final notes here. The indicial roots, the values of those actually tell us about what types of solutions we're actually going to get. And once again, we're always assuming x sub 0 equals 0. So case 1, R1's greater than R2, and R1 minus R2 is not a positive integer, so it's like a fraction. Then we're going to get two linearly independent solutions, and that's the two examples we looked at, and those are the examples we're going to focus on. Case sub 2 is that R1 minus R2, so the two roots, is actually a positive integer. Then there's going to exist two linearly independent solutions, and the first one, this is what we've been dealing with, so we get the y1, but notice what happens with the y2. It's a much more complicated form here. We've got some constant times y1 times the natural log of x, and that's plus this summation of b sub n times x to the power n plus r, the second root, r sub 2. And once again, b sub 0 can't equal 0 in this case. All right, that's not a situation we're going to talk about, but that's one of the possible solutions. And then the last case, that's when R1 equals R2. So this would be if we get the exact same roots, so our indicial equation gives us like 2 and 2 or something like that. Then we do get two linearly independent solutions, but y1 is going to equal this, and y2 is going to equal this, but the problem is that method of Frobenius doesn't actually give us that second solution. So we're basically going to avoid case 2 and case 3. You can take an upper level course to figure out, all the details of all that. All right, so that is the end of example 2.